bright, dark, bright.
So in this previous video, I introduced a way to train your own speech commands model and use it on the M560 or any ESP32 board with a microphone. It is a very easy to use method, especially for beginners. And after that, I saw many Tinkerdoodle users were able to train the model and use it on their own device. So after that, I also got quite a few questions from some users that they were wondering how this speech commands model works internally. So here I make a new video to explain the internal implementation details of the speech commands recognition on ESP32.
Right.
The first question I got to ask is, how does speech commands recognition work on ESP32? Because we know ESP32 is a very power-constrained device. How can we make it actually work, especially on real time? The answer is that it is a two-step process to recognize a speech command. For the first step, we extract the audio signal from the microphone and call a library, a FFT, fast Fourier transformation library, to convert the audio signal into spectrogram. This step basically converts the audio into an image of dimension 12 by 61. This image represents the signal, the audio signal in 1 second. And then we feed the spectrogram into a CNN, a convolutional neural network, which then converts the spectrogram into a list of labels, each with a probability. So how can we make that work on ESP32? For the extract audio signal part, I use a library, a module called I2S, and for the convert the audio signal into spectrogram and feed that into CNN to run it through the neural network, I use a library called neural network on microcontroller. At the time when I did the speech commands model, neither of those two modules were in the MicroPython official firmware. So I have a script to build a customer MicroPython firmware including those two modules. And after that, for all other Tinkerdoodle users, they can just deploy the neural network model and call it right from the MicroPython code. They don't have to worry about either the FFT library or the CNN inference. The second question I got asked is, how can we train the model using very few samples? Because we know that for any deep learning model training, it requires a huge amount of samples. But in my method, you only need about 100 samples to get a decent model. So how is that possible? The answer is I use a transfer learning. So what is transfer learning? Let's first look at the full CNN model. That you can see it's a sequential model with multiple layers. It has multiple convolution layers, followed by ReLU activator, and followed by the max pooling layers, and has multiple iterations of that. And at the end, it has a dense layer, and basically to calculate the score of each label, and a soft max layer that converts the scores into probabilities. With transfer learning, we can train the base model using many samples, as many as we can get, so that it can train all those layers with good precision or accuracy. And at the end, we get rid of the last two layers from the large model, and we can retrain those two layers using few samples. So that's the idea of transfer learning. Basically, you train the base model, and after that, you remove the top layer. That basically means you use the remaining layers to behave as a feature extractor, and you train your delta model, which is basically one layer plus a softmax as a simple classifier on top of the base model. So to train the Google speech command set, to train the base model, I use the Google speech command set, which contains more than 60,000 samples. This training was done on a machine with GPU. Using TensorFlow, the model training was done within an hour. You can notice that the 60,000 samples is actually not a huge number compared with other deep learning tasks. But because what we're doing is just like 1 second speech command recognition, 60,000 samples are good enough to train a base model. Compared with that, the delta model requires far fewer samples. That you can just provide up to 100 personalized audio samples 1 second each, and you can do the training right within browser using TensorFlow.js. Once you have the delta model, it is easy to just dump out all the weights in the dense layer and deploy that to the ESP32 device as a MicroPython module and run it. So that's basically the idea behind both the model inference on ESP32 and the model training of the speech commands model. If you find this video useful, and if you want to play more on this topic, I provide a few references. So here I want to give a special thanks to the neural later work on microcontroller module. This library is available on GitHub. It not only provides a very stable implementation of the model inference on microcontroller, but it also comes with a few samples, of which one of the samples, the keyword spotting sample, actually inspired my speech commands model project. So hopefully, if you play with it, you can also get inspiration too. Okay, that's all for this video. Thanks for watching.